Hi, everyone, and welcome to my next installment in this pre-calculus algebra series of videos. In this one, I'm going to talk about a new type of function that we haven't talked about in previous videos, the exponential function. Now, what makes an exponential function different from, say, a polynomial or linear, or quadratic, or rational function is that the variable appears as an exponent. So the general form of an exponential function will be some number, I'm going to call it b for base, raised to the power of x. All right, b to the x. Now, there's a couple of restrictions on b. B can't be any number, but b has to be positive. Right? If b is negative, we run into problems when we're graphing. Right? Because a negative raised to an even exponent is positive, a negative raised to an odd exponent is negative. Sometimes a negative raised to a rational or fractional exponent doesn't exist. So there's all kinds of issues when the base is negative. So base has to be positive. And also, one other restriction, we're not going to use the number 1, right? We're not going to say 1 to the x. And the reason why is because, let's say we have y equals 1 to the x. Well, 1 to any power is 1, so that becomes just 1, which is a straight line, horizontal line, right? So we're not going to use 1 as our base, but any other number. So, for example, some exponential functions, f of x equals 2 to the x. G of x equals 4 to the x plus 3. Right? We could talk about transformations of graphs, shifting, reflecting, stretching. So it's not just going to be a number to the power of x. Let's say h of x is equal to -3 times something to the x. Now that number doesn't have to be a bigger than 1. It could be a fraction. Let's say 2/3 to the x. All right, so an exponential function is where your variable only occurs as an exponent. So what I'm going to do in this video is talk about some of the general things that we've talked about previously for other types of functions, what the graphs look like, evaluating, plotting points, domain and range, things like that. Okay, so one more time, exponential function is a function in which your variable appears only as an exponent. All right, so let's look at some specific examples. And let's start with the graph. And then after we graph, let's talk about the domain and the range. Okay, so let's use as an example, f of x is equal to 3 to the power of x. Now, if you go back to way back on this playlist, when we first started talking about functions and graphs, the first approach we took to graphing was the least sophisticated method, which was plotting points. Right? Plug in a bunch of x values, get some y values, and plot points one at a time until you get a feel for what that graph is going to look like. So let's take that approach. Okay. If x is 0, the y value would be 3 to the 0, which is 1. All right, so that's 1 point on the graph, 0, 1. Okay. If x is 1, we get 3 to the first power, which is 3. So that's the point 1, 3. Okay, keep going. If x is 2, we get 3 to the power of 2, which we know is 9. So that's the point 2, 9. 2, and now we're up here at 9. Right, so this is 0, 1. This is 1, 3. This is 2, 9. All right, so let's just do a couple more. When x is 3, you get 3 to the third power. 3 times 3 times 3 is 27. Okay, problem. My graph only goes up to 15. So there's going to be a point up here somewhere at 3, 27. All right, so I'm going to stop plotting points. Let's just do maybe one or two more points. When x is 4, you get 3 to the fourth power. 3 times 3 times 3 times 3, which is 81. And maybe one more. When x is 5, 3 to the fifth power, which is 243. So these points definitely don't fit on this graph. All right, so what happens with an exponential function is that the y values get really big really fast. Really big, really fast. Well, let's look at negative exponents or negative values of x. So if you plug in a negative number, it's going to be a negative exponent. So x and f of x. So when x is negative 1, you get 3 to the negative 1 power. Negative exponents mean reciprocals. So that's 1 over 3. Okay, so when x is negative 1, down here at negative 1/3. Negative 1 comma negative 1/3. All right, and let's just do the same numbers. Negative 2, negative 3, negative 4, and negative 5. So when x is negative 2, you get 3 to the negative 2 power, which is 1 over 3 to the second power, which is 1 over 9. When x is negative 3, you get 3 to the negative 3 power, which is 1 over 27. We're getting the same numbers as we got over here on the left, just the reciprocals. When x was 4, we got 81. When x is negative 4, we get 1 over 81, right? Negative sign means reciprocal. When x was 5, we got 243. When x is negative 5, we get 1 over 243. Right? 1 over 243 is, if we round it, it's about 0.004. Right? 1 over 81 it's about 0.01. You could verify this on a calculator. 1 over 27 is about 0.04. 1 over 9 is, if we round it, it's about 0.11. And 1 over 3, it's about 0.33. So as the x values get more negative, the y values are getting closer and closer to 0. So what happens is the graph sort of levels off at 0. And what we see here is a horizontal asymptote at 0. The reason we have a horizontal asymptote, a leveling off of the graph, is because we're taking the number, we're looking at the original function, 3 raised to a power. Anytime you take a positive number, raise it to an exponent, you're going to get a positive number back. The y values are never going to be 0. The y values are never going to be negative. So for every y value, you're going to get a positive number. For negatives, as you get more negative, the y values get smaller. So say more negative, y values are getting smaller. As the x values get more positive, the y values are getting bigger. All right, so this is the graph of 3 to the x, and it's going to look exactly the same, very slightly differently if it was 2 to the x or 4 to the x or 5 to the x or 7 to the x. Right? On the right-hand side, the y values get real big real fast. And on the left-hand side, the y values get real small real fast. Okay, so if I go back to the previous slide, and I'm looking here, the number we're raising to the x, that's b. B is the base. It's got to be bigger than 0. Got to be bigger than 0. So this is like the number line for b, our choices for b. But it can't be 1. So let's just put an open circle at 1. So our values for b could be anything in here between 0 and 1. Anything over here from 1 to infinity. So the problem we just did on the other slide was over here. F of x is equal to 3 to the power of x. That's to the right of 1. And it turns out all of those values of b, graph is going to look the same. It's going to go through the point 0, 1, because anything raised to the 0 power is 1. It's going to get small on the left. It's going to get big on the right. Now, what if we pick a value of b that's less than 1? So let's say g of x, instead of 3 to the x, let's say 1/3, 1/3 to the x, for example. This is just an example. So what does the graph of 1/3 to the x look like? Let me go to a fresh slide. If we do the same thing, we're actually going to see the same numbers as on the previous slide. I'm going to set it up the same way. I'll use 0 up to 5, and then we'll look at negatives, -1, -2, -3, -4, and -5. So when x is 0, you get 1/3 to the 0, which is 1. Right? Anything to the 0 power is 1. So just like before, the graph is crossing through the point 0, 1. That's the y-intercept. When x is 1, you get 1/3 to the first power, which is 1/3. When x is 2, you get 1/3 to the second power, which is 1/9. 3 times 3 is 9. When x is 3, you get 1/3 to the third power, which is 1/27. 1 to the third is 1. 3 to the third is 27. 1/3 to the fourth power is 1/3 to the fourth power, so 1/81. And when x is 5, 1/3 to the fifth power, 1/243. We can keep going. But these are the same numbers we got on the previous slide, on the previous example with 3 to the x. But these were the numbers. Let me go back a slide. These numbers: 1/3, 1/9, 1/27, 1/81, 1/243. Those are the numbers we got for negative x values. For the graph of 1/3 to the x, I'll go back to the other slide. We're getting those same numbers: 1, 1/3, 1/9, 1/27, 1/81, 1/243. But we're getting those for the positive numbers. So it's sort of the opposite. Now, when x is -1, we get 1/3 to the negative 1 power. A negative exponent means reciprocal. Right? The reciprocal of 1 over 3 is 3 over 1. When x is negative 2, we get 1/3 to the negative 2, which is the reciprocal, 3 to the positive 2, which is 9. When x is negative 3, we get 1/3 to the negative 3 power. Again, negative means reciprocal, so that's 3 over 1, or 3. Maybe we don't need parentheses. To the 3rd power, 27. Hopefully these numbers are looking familiar because they're also the same numbers we got on the previous slide. 1/3 to the 4th power is the reciprocal, negative 4. The reciprocal of 1/3 is 3 to the 4th power, which is 81. And then one more. 1/3 to the negative 5th is 3 over 1 to the positive 5th, which is 243. So now we're getting the same results, but sort of on opposite sides of the y-axis. So now for negative numbers, the graph is getting big. And for positive numbers, the graph is getting small. Still, we have this horizontal asymptote at 0. 3 is a positive number. 1/3 is a positive number. When you take a positive number, raise it to an exponent, you always get a positive number back. So raising it to the power of x is how you get your y values. So a positive number to the power of x is always positive. So the y values are always positive. So for both of these functions, if we look at the domain and the range, well, the domain is going to be all real numbers, negative infinity to infinity, right? The domain is the set of numbers you're allowed to plug in for x, right? X is an exponent. Exponents are allowed to be negative. Exponents are allowed to be positive. Exponents are allowed to be 0. You could plug in any number you want for x. The range, however, is not all real numbers. The range are all the output values. Or if you're looking at the graph, the range is the set of all the y values, all y values that appear in points on the graph. So if you look at this graph and also the graph on the previous slide, the only points that appear on the graph are above that horizontal asymptote, above 0. So the range of an exponential function will be horizontal asymptote up to infinity, 0 to infinity. Now, sometimes the range will change if we start shifting or moving the graph around. If we apply transformations of functions, and then the range might not be 0 to infinity. So generally, our base is going to be a positive whole number, or a positive rational number, a positive fraction, a positive whole number. With one exception. So let's look at, again, we're sticking with the exponential functions. F of x is equal to b to the x, where b is positive and b is not 1. B is positive and b is not 1. Now, there's one irrational number. One irrational number that we're going to use for the base. Very important irrational number. And it comes from this other function. I don't want to talk too much about this because this is something you're going to get into in Calculus 1. But since we're going to be using this new irrational number today, I'll just very briefly talk about where it comes from. we have this function y equals 1 plus 1 over x to the power of x. This is not an exponential function. Even though x is the exponent, exponential functions, the variable is only occurring as an exponent. Here we have an x as an exponent. We also have this x down here. So it's sort of a combination of rational and exponential functions. So this is not strictly exponential, but we've talked plenty in previous videos about evaluating functions, plugging in x values. So if we plug in some x values, and I'm not going to use 1, 2, 3, 4, 5. I'm going to use 1, 10, 100, 1,000, 10,000, powers of 10, 100,000, and so on. Right? So as the x values go into this function, as these x values go into this function, what happens is these y values start getting closer and closer to this infinite decimal, this never-ending decimal, 2.718 something something something. Normally we may be rounded to 3 decimal places. Now this number is a really special number in mathematics. Not just mathematics, but biology, geology, anything that has to do with the existence of natural or living things. It comes up all over the place in nature. It's an observation. It's something we see happen. It's not something we do. It's something we observe in nature. Whether it's a colony of bacteria, a crystalline structure, a population of gazelles in the plains of the Sahara, I don't know. But we see it happen a lot, naturally. So we call this number E. And E, lowercase e. Now this is like pi, right? There's a button on the calculator. There's a pi button, there's an E button. E is called the natural exponential base. The natural exponential base. It's approximately equal to 2.718. It's not exactly, but if we round it to 3 places. And so as in this function up here, as the x values get larger and larger and larger, when you take calculus 1, you're going to call these limits. The limit as x goes to infinity. But for right now, we're not using the terminology limits. As x gets really, really big, the y values get closer and closer and closer to this constant E, which is approximately 2.718. So we've just graphed 3 to the x and 1/3 to the x. So what does the graph of e to the x look like? Well, it's bigger than 1. E is bigger than 1. E is 2.7 something, right? So E is bigger than 1. So the graph looks exactly like 3 to the x. Right, it's probably a little steeper than that. right? Horizontal asymptote at 0. Right? Whether it's 2 to the x, 3 to the x, 4 to the x, 8 to the x, 11 to the x, they all look like this. They all look like this. E to the x looks like this. So this would be the graph of f of x is equal to e to the power of x. I'm bringing up this number e now because we're going to be using it later in this video, also in the next couple of videos as well. Okay. So when we first started talking about functions earlier if you go back about 12 videos, 15 videos back, we start talking about functions. Some common characteristics. We talk about domains and ranges, what it means to evaluate, what it means to graph, things like that. So let's evaluate a couple of functions. Expressions, I should say expressions. These aren't functions. These are our expressions. So approximate each number. So we're approximating, which means rounding, right? Round to the nearest thousandth. The only way to do this is with a calculator. There's really nothing else we could do here. So first one, 2 to the power of the square root of 6. So this is like saying f of x is equal to 2 to the x, and evaluate what is f of the square root of 6. Well, that's going to be 2 to the square root of 6, and it's going to equal something. We're going to have to round it. Second one, g of x is e to the x, and we want to evaluate g of negative 1.79. So that's going to be e to the negative 1.79. And it's going to be approximately equal to something. And again, we're going to get that from the calculator. So let me go ahead and pull up a calculator. It's the only way to do this. So over here on the right, you have the caret button. That's for exponents. So if I want 2 to the square root of x, I'll hit 2 to the power of, so that's caret, 2 to the power of, and now I need the square root. Well, there is no square root button on the calculator. There's no square root button. But you see the square root over here on the left-hand side, the square root is it's above the x squared button. It's written in blue. Anything above one of the keys on the calculator, you need, if it's written in blue, second. So second, and then I'll hit the x squared button. And now you see on the screen an empty square root. So I'm going to go ahead and hit 6. So now I have 2 to the power of the square root of 6. Enter. And we've got about, if we're rounding to the thousandth, that's 3 decimal places. It looks like about 5.462. All right, so while I still have the calculator up, let's do e to the x. There is no e to the x button on the calculator, but just like the square root, it's written in blue above a different button. So on the left-hand side, you see this button that says ln. ln. We haven't used that yet in any of the previous videos, but we will be using it in the very next one. So for right now, we don't need to know or worry about what ln stands for, but we do need e to the x, which is above the ln. So I'll hit second, then I'll hit the ln key. So now on the screen, you see e with an empty exponent. So I'll go ahead and type in negative sign. So negative 1.79. All right, so we get about, if we're rounding into 3 decimal places, it looks like 167.1669. If we keep 3 decimal places, that'll round to 1.67. All right, so we got when we rounded, we got 5.462 approximately and we got 0.167. Okay, so we can evaluate, meaning plug in a number for our exponent using the calculator. All right, I have a few more problems I want to do. Let's see. So, graph. Graph the function h of x equals 2 to the power x plus 1 plus 2. So we're going to use transformations of the graph of f of x equals 2 to the x. All right, so we're going to start with this guy, which we've already talked about. And we're going to use that graph to graph this one I have highlighted, which is h of x. And we're going to graph it and make sure we put the asymptote in the right place. We'll talk about the domain and the range. So let's start with the graph of 2 to the x. 2 to the power of x has an asymptote at y equals 0. So the equation of that asymptote is the line, the horizontal line, y equals 0. So now let's look at the function h of x is equal to 2 to the power x plus 1 plus 2. Well, we can apply what we already know about transformations of graphs. That's not something I'm going to reteach or re-explain in this video. If you're unsure about transformations, maybe pause this video now, go back to my video on transformations of graphs, vertical shifts, horizontal shifts, reflections, stretching, compressing. Then come back to this one. So what we want to do is I'm going to graph h of x in blue. So I want to start with the red graph, do something to it, and end up with the graph of h of x. So the question is, what does the plus 1 do? And also, what does the plus 2 do? Right, if we know what those two things do, we could apply them to the graph of 2 to the x. Well, it looks like we have a horizontal shift and a vertical shift. So shifting is a result of addition and subtraction. So when we have addition or subtraction in here inside the function, this is the exponential part of the function, 2 to the power of. Well, that's going to shift to the left 1 unit. That's going to take everything on this red graph and move it left by 1. Then we've got a plus 2 on the outside, not part of the exponential part of the function. That's going to be a vertical shift, shift in the y direction. So the entire graph is going to shift up by 2 units. All right, so we could look at this one point, this point 0, 1. If we move that, we can move the rest of the graph, right? So we're going left 1. And then we're going up 2. Left 1, up 2. So now we've got our point. 1 point on the graph of h of x. Now, when we're shifting, the asymptote moves as well. The asymptote comes with the graph. So when you take that horizontal asymptote and shift it to the left or the right, when you shift that asymptote, that dotted line left or right, it's still in the exact same place. But when you move it up 2 units, it's now going to be at the y value of 2. And so the rest of the graph follows. And so in blue, we've got the graph of h of x is equal to 2 to the power x plus 1 plus 2. The domain of any exponential function of the form b to the x, or some transformation of b to the x, is all real numbers, negative infinity to infinity. And the range, as I mentioned earlier, is everything above the asymptote, unless there's a reflection. If it's, if the graph is reflected down, then it's everything below the asymptote. But we didn't reflect the graph here. We just moved it. So everything above the asymptote would be 2 to infinity. Okay, 2 to infinity. Let's see what else we got here. Similar problem. Very similar problem. We have f of x and g of x. We want to graph g of x. This is our goal. Graph this function. By first graphing f of x. Right, so this is a more basic version. This is 1/3 to the x. We want to use this to graph 1/3 to the power of x minus 4 plus 3. So 1/3 to the x, that's something we've already graphed earlier on in this video. Instead of going up to the right and down to the left, it's the opposite. It goes up to the left, down to the right, asymptote at 0. And so just a slightly different starting point. And now we've got g of x is equal to 1/3 to the power x minus 4. All that plus 3. So we have more or less the same situation. We've got something going on up here. So what does the minus 4 do? And then we've got a plus 3. What does the plus 3 do? Well, it's just similar to the last problem. Horizontal shift and a vertical shift. So that minus 4, which is part of the function, part of the exponential part of the function, that's going to shift in the horizontal direction. We always do the opposite sign for horizontal. So shift the entire graph to the right 4 units. And then the plus 3 on the outside of that exponential expression is going to be in the vertical direction. So shift up. Three units. So we could take the same approach as before. You could take this point right here and move that point, and the rest of the graph will follow. Right, so we're going to go 1, 2, 3, 4 to the right. And then up 3. 1, 2, 3. So that red point is moving to right here. Right, so that's the point 4, comma 4. Started off at 0, 1. Move that point to the right, 4, up 3. Now we're at 4, comma 4. Since we went up, the asymptote has to move up. Right, so the asymptote is moving up 3 units. So instead of being at 0, let me go back to blue. Instead of being at 0, it's up here at 3. And the rest of the graph follows. So down to the right, up to the left. So it's an exact copy of the red graph, just in a different location. Different location. We shifted it to the right, we shifted it up. And then we draw our exponential graph, make sure it sort of levels out at that asymptote. All right, I think I have one more problem I want to go through. Okay. So now an application. So suppose you have $1,900 to invest. Which of the two rates would yield a larger amount in 4 years? 12% compounded daily or 11.94% compounded continuously? Okay, we can't answer this question. We need a little bit of background and some formulas. So one application of exponential functions is interest. Anytime you borrow money, there's a fee. And that fee is given in terms of a percentage usually. It's called interest. And now interest, okay, so interest is an amount of money you have to pay for borrowing money. How much interest do you have to pay? Well, it depends on a number of things. It depends on how much you borrow. When I say you, I mean that could be a person, you, it could be a bank, it could be anything. Anyone or any entity borrowing money. So it depends on how much is borrowed. We call that the principal amount. So I'm going to use P for that, capital P. Capital P stands for the principal. Another word for principal is starting amount. Right? P is the principal amount or the starting amount. So for this problem, suppose you have $1,900 to invest. Okay, P is 1,900. It also depends on the percentage rate. Well, what are you being charged? What percentage of your principal is being charged? Well, it's the annual interest rate. So for interest rate, I'm going to use lowercase r. This has to be given as a decimal, right? Not a percentage. Remember, percents are not numbers. So for example, if the interest rate is 12%, then R, we would have to convert 12% to a decimal. So divide by 100, R would be 0.12. So this is an example. The amount of interest that is charged also depends on how long you owe the money for. investing $1,900 for 6 months, for 1 year, for 5 years, for 10 years, for 20 years. In this case, it's 4 years. We have to be consistent. So time will always be measured in years. Time is always measured in years. So for example, for years, we would use t equals 4. Something like 6 months, we would use t is equal to 0.5. 6 months is half of a year. So 6 months would be half a year, 0.5 years. It also depends on how often interest is recalculated. Right? So when a bank, so if you think about a credit card, every month you get a bill in the mail or an electronic bill, either way. You get a monthly statement. If you have a bank account, you get a monthly statement. That means once a month, the bank is recalculating how much interest you owe or how much interest they owe you. Either way, calculating interest periodically is called compounding. So if you look at the problem, you see the word compounded a couple of times. You see compounded daily, you see compounded continuously. So the number of compounds per year is going to affect how much interest there is. So we're going to use lowercase n for that. The number of compounds per year. So for example, if the problem says compounded monthly, $12 months in a year, so that happens 12 times in a year, n would be 12. If it said you're doing a different problem and it says compounded weekly, well, there's 52 weeks in a year, so n would be 52. Compounded annually, the word annually means once a year. Let me spell that right. Annually means once a year, so n would be 1. I'll say etc. I'm not going to list them all, but quarterly would be 4 times a year. In this problem, it's daily. And so which of the two rates would yield the larger amount in 4 years? Right, so we have basically we have 2 options here, option A and option B. In both cases, you're investing $1,900 for 4 years. Now you have 2 interest rates here. Option A, 12% compounded daily. So 12% would be 0.12. And then the other one is 11.94% compounded continuously. We have to talk about what continuously means. 1194 for the 11.94%. Okay, so option A is compounded daily. That means once per day. So in a year, it happens 365 times. I'll come back to option B in a moment here. Let me just finish this list over here on the right. And the fourth, or the final variable we need. How much do you owe in the future? That's, of course, that's important. So capital A, we're going to use for the future value. So you're starting with P dollars. You're ending up with A dollars, right? Starting and ending. And how you get from beginning to end depends on the interest rate, how long, how many years go by, what kind of compounding it is. Right? So in both of these cases, we're trying to determine if the first option or the second option is better. Right? So A is the question mark, which would yield the larger amount, which ends up with more money. Okay. This is a very brief explanation of this idea of interest. So, I mean, I could spend an hour and a half talking about the intricacies of where these formulas come from and deriving them and whatnot, but I'm just going to give you the formula. So for compound interest, what we have over here on the left, we've got 5 letters, and they're all related to each other. How much you start with, how long the money sits there, what the interest rate is, how many times a year interest is being calculated, what is the final value. All these values are connected. And the amount you end up with is going to be equal to the amount you start with times something. And it's going to be times something bigger than 1, because the final value is going to be above or larger than the starting value. So it's going to be, you take the starting value and multiply it by, 1.3 or 1.05, 1.228. And you're going to multiply it by something a little bigger than 1. Okay. Specifically, you're going to multiply by 1 plus R over N, because we're taking that annual interest rate and splitting it up N ways. So if it's monthly, you divide the rate by 12 to get your monthly interest rate. If it's weekly, you divide R by 52 to get your weekly interest rate, and so on. And then you're going to multiply that, or sorry, raise that to the power of N times T. And that's why we're talking about this in the context of exponential functions, because this is an exponential function. What is changing over time? What are the variables? Well, A, the amount you owe is changing over time. As time goes on, that value goes up. So time is also a variable. Those are the 2 variables. The other letters, those are fixed. They never change. Your starting value is your starting value. Your interest rate is your interest rate. Number of compounds per year is set from the beginning. The only 2 things that are changing are time and then the future value, which depends on time. Okay, so this is an exponential function. So what we're basically doing is let me use red. We're taking the numbers that are given in the problem and plugging them into the formula. Replace P with 1900, replace T with 4, replace R with 0.12, replace N with 365. Okay, so we'll get to that. The other type of interest in which there is no time between recalculating interest, right? It doesn't happen once a year, twice a year, 12 times a year, 52 times a year. It happens at every instant, continuously. So when you see the words in the problem, compounded continuously, like you got to see those words. So when you see those words, we have a slightly different formula for calculating the future value. There is no n. Notice there's P, T, R, and A. There's no n. So for continuously compounded interest, again, the explanation uses a little bit of calculus, this idea of limits. So as the value of n goes to infinity, this formula starts to sort of change, and the number e starts to emerge. I'm not going to do it. It's a little outside the scope of this course, but as the number n gets infinitely large, this formula on the left becomes p. It's still p being multiplied by something larger than 1, but we're going to utilize the natural exponential base, e, the number e, raised to the power of r times t. And so these are the two formulas for interest, for future value of an account that has interest. Now, when to use which one? Well, it depends. It depends on what words you see in the problem. Compounded daily, monthly, yearly, annually, biannually, semi-annually, weekly. We're going to use this guy down here. But when you see the words, and again, this has to be given explicitly in the problem. When you see the words compounded continuously, you are going to use the formula for continuously compounded interest. Now, this formula is not just used for interest, it's used for other things. We're using it here in the context of interest, but it's a continuously changing quantity. So now, whichever formula we're applying, it doesn't matter. We do the problem the same way. We take the given information and substitute it into the equation. So let me bring up the calculator, because this is definitely a job for the calculator. So on the left, actually, before I bring in the calculator, let's plug in some numbers sort of visually. So we're going to do A is equal to P, which is 1900, parentheses, 1 plus the rate 0.12 divided by n, which is 365. I'm going to raise that to the power of n times t. So 365 times 4. I'm just replacing each letter with the corresponding number. And then on the right, for the option B, continuously compounded interest, A is equal to 1900 times E to the power of 0.1194 times 4. Right? This is going to go into the calculator, and it's going to give us a dollar amount. Right? This is going to go into the calculator, and it's going to give us a dollar amount. Just looking for which one gives us a bigger number. All right, which one gives us a bigger number? So for the first one, let's do 1900 parenthesis 1 plus, I'm just typing in exactly what I see on my screen. 1 plus 0.12 divided by 365, close parenthesis, raised to the power of 365 times 4. All right, so I literally just typed in exactly what I have written in blue. All right, we get $3,070, and if we round to the nearest penny, it looks like $3,070.30. And then for the other one, 1900, so 1900 times E. So that's above the ln key. So you see that in blue on the left-hand side. So I need second ln e to the power of 0.1194 multiply by 4. And we get a slightly smaller dollar amount. So question, which of the two rates would yield the larger amounts? Looks like the first one. 3,070 and 30 cents. Option B with the continuously compounded interest rate, $3,063.18. Now, this is a good approach. Right, let me erase these arrows. It's a little bit cluttered. Oop. There we go. So this is a good approach. This is how I like to sort of systematically get through these problems. Sometimes you're going to use two different formulas. Sometimes you're going to use one formula in one problem. Either way, it's a good approach to take the numbers from the problem and sort of generate this list of numbers that correspond to each variable, and then plug those into the formula, write it out, and then type that into a calculator, and you'll get your answer. In this case, it was 3,070 and 30 cents. Other one gave us $3,063.18. So what is the final answer here? It's not either of those numbers. The final answer is 12% compounded daily is better. Right? That's the better option if it's money you're investing. Now, the answer would be the other one if the question said you're borrowing money, right? So better depends on context. All right, this is an investment, so the better option is the higher number. If the question said you have to borrow $1,900, which is the better option, it would be the yellow one, the smaller number. All right, so that does it for this video. I'm going to talk more about exponential functions in the next one, but we're going to also transition to the next topic, which is logarithms. But that does it for this one. I hope this was helpful.